which is going to be our natural solution. So for those of you taking differential equations, this is the same thing as your homogeneous solution, or some of you call it a homogeneous solution. And it's one that you're just going to look at the formula for after you compute alpha, omega naught, and S. And alpha, before you even write the equation for it, what I want you to think of with alpha is the bigger the alpha, the more strong the damping coefficient is. So the bigger the alpha, the longer it will take to damp out. You can think of it sort of like a time constant. If alpha is really huge, it means the resistance in your circuit is really huge, and whatever the circuit does is it's going to take forever to even out. That means it's not going to oscillate. It's going to do, it's going to do one of those long, thin lines. This is for a big alpha, much, much greater than your omega naught. And then similarly, your omega naught says how much, so your alpha says how much does your circuit want to slowly come to a final position. If your omega naught is really big, it means that it wants to oscillate a lot, and it wants to try to get to its initial condition really, really fast, and it's going to oscillate around there. So that's going to be a big omega naught. And if they happen to be the same size, it will get to be your final position as fast as possible without oscillating. So that's for your omega naught equaling your alpha. And we call that critically damped. And we call, if you've got some sort of huge alpha, we call that overdamped. And if you've got some really big omega naught, we call that underdamped, which is the same thing as saying it oscillates. So the intuition that I want you to have when you're thinking of all of this is that if alpha is greater than omega naught, it's not going to oscillate, and it's going to be overdamped. If they're the same, it won't oscillate, but it'll be right on the verge of oscillating, and it'll be critically damped. And if your damping coefficient is small compared to your omega naught, then it will oscillate like crazy, and it will be underdamped. And the bigger the omega naught compared to the alpha, the bigger it's going to oscillate, and the faster the frequency it's going to oscillate. So now, armed with all that, now with the intuition, it's just the equations. And to find the equations, we're going to have to draw the circuit again. There's a lot of redrawing circuits. So to draw the circuit this time, we're going to draw it for time greater than 0. And time greater than 0, what is the voltage source look like?
So the voltage source is going to be 24 volts.
That's it. And tell me about the capacitor and the inductor. What do they look like for time greater than 0? For any time greater than 0.
So it's like we have to include an inductor, like one.
That's it.
And then the capacitor as well.
They're doing their things. And because the switch is open and I'm not asking questions about what's happening with the switch, well, I could draw this again. It doesn't really get me anything because I'm really interested in what's going on around that capacitor. I really want to find everything to do with B sub C. That's what I'm being asked to find. So is this equation, our equation for alpha, depends upon whether or not whether or not the circuit is in series or parallel. So Ben, just finishing it up, is this in a parallel or series?
This is in series.
Could not be more in series if you tried. So now we can just read out the equation for alpha, which is R over 2L, which for this particular problem is 2.5. Our omega naught is always going to be, regardless if it's in series or parallel, 1 over LC. And these equations come from solving the differential equation, which we'll do more of in our next class, Signals and Systems. Now our S, we create our S by this equation. which is always the same whether or not it's in series or parallel. And for now, we'll develop a deep intuition for what S means in our signals and systems class. For now, just realize that there is no intuition behind it for this class, and realize that it's got two parts. It's got this first part and it's got the second part. And the second part might be real and different if alpha is bigger than omega naught. It might be 0 if they're the same and it's critically damped, in which case you'll have two values of S. Or if alpha is less than omega naught, we'll end up having a negative square root, which gives us complex conjugates. And if we get complex conjugates, the imaginary part of those complex conjugates is equal to our omega sub d. And that does have a physical significance. That is how much the circuit will actually oscillate. So again, if S has complex conjugates, it means that omega naught must be bigger than alpha, which means that it oscillates. And what frequency does it oscillate? It oscillates at the imaginary portion of what our S is. That's our omega sub d. Does this circuit oscillate? Dom?
I'm sorry, sir, I wasn't paying attention
Yeah.
to that last part.
Does this circuit oscillate? Our alpha is 2.5, our omega naught is 2. Does it oscillate?
No, it does not. It's overdamped.
That's right. It's overdamped. So we're in this category. And if we're in that category, each of these three categories have pre-made equations that come from our differential equation solution. And the pre-made equation for V sub C, you just read it off from my handout or from your readings, which is C1 e to the S1 t plus C2 e to the S2 t. And for this particular problem, our S's are going to be minus 2.5. I'll just, wait, even better, I'll just write down what they are. They're going to be equal to minus 1 and minus 4.
So, sir, if those are non-real, that's when you would use the C1E S1T plus C2T E S2T?
No. When these things are unique and real, they are overdamped. If they have an imaginary component, which is what you asked, then they would be complex conjugate and they would oscillate. They would be underdamped and you'd end up having sines and cosines. You'd end up having...
That's right. So is it when it's a repeated root, then you use the...
That's right.
Extra T in the second...
That's right. So what Dom is talking about is you're going to use this if you've got two different roots. If they are overdamped, you'd use V, these are all V naturals. You'd use this, and now I'm just going to say S because if it's critically damped, it'll have the same, there is only one S if it's critical. And then it would be, let's see, what's the neatest way to write this? E to the minus alpha
T, right?
C1 cosine of omega sub d t plus C2 sine of omega sub dt. There we go. And that's if it's underdamped. So we are going to be doing this one again. So therefore, our overall equation is going to be, oh, and by the way, and this alpha, just like omega sub d is the imaginary part of S, the alpha is equal to the real part of S. But you don't need to find it out because you already found it in this first section. Okay, so our V sub n for this particular problem is going to be C sub 1 e to the minus t plus C sub 2 e to the minus 4t, since we found our roots of S to be -1 and -4. Questions on that section? So now we've got two unknowns here, and we have
Are those S values rounded or are they strict integers?
particular problem. They're exactly equal to -1 and -4 to the nth degree. But I mean, we can figure it out. If it's exactly -1 and -4.
Okay, thank you.
But in general, they could be any number. We have these two C1s, two unknowns, C1 and C2. And we have these two initial conditions, VC and VC prime. Should we substitute in our initial conditions right now and find out what these unknowns are, C1 and C2?
We should find the force
What do
solution.
you think, Connor?
Wouldn't we just plug in t equals 0?
So I think I heard Jonathan say, let's solve for C1 and C2 by using these initial conditions, right? Was that Jonathan? I couldn't tell.
Yeah, that was me, sir.
So you don't like these C1 and C2s. You want to find out what these things are. And what do you think, Connor?
You need to find the force solution at t equals infinity.
Yeah, that's it. You will eventually do that, Jonathan, but not yet. You got to firstly find what the force solution is.